So in this video, we are going to continue solving our problems from exercise 9.2 and we are going to see here problem number 2. So let's see what the problem number 2 is. If E, F, G and H respectively, the midpoints of the sides of a parallelogram ABCD, then show that area of EFG is half the area of ABCD. So let's try to visualize the question that has been given to us. First of all, we need to draw a parallelogram ABCD. So I'm going to try to do that. This is our parallelogram ABCD. So let's try to name it A, B, C, and D. Okay. Now let's read the question. If, sorry, okay. So if E, F, G, and H are the midpoints of the sides. So let's mark these midpoints by different color. So let's say this is the midpoint E, this is the midpoint F, this is the midpoint G, and this is the midpoint H. Okay, and this is my vertex D. Okay, so E, F, G, H are the midpoints of the sides of the parallelogram. Then we have to show that area of EFGH. So EFGH is one quadrilateral. So that area is half the area of this whole A, B, C, D. Okay, so this is what we have to prove. So let's see how we can approach this problem. Now, the first key information that is given to us is these are the midpoints of the sides. Okay, so let us assume we know that in a parallelogram the opposite sides are equal to each other. Okay, so I'm going to say step number 1, let AB, which is equal to CD, be equal to 2x. Let the length of AB and CD be equal to 2x, and let AD, which is equal to BC, because opposite sides of parallelogram, let that be equal to 2y. Okay, so now these are the midpoints of 2x. So what will be the length here? So this is going to be x, this is going to be x, because E is the midpoint, E is the midpoint of AB, and AB is 2x. Okay, similarly this is going to be x, this is going to be x, and this is going to be y, this is going to be y, this is also going to be y, this is also going to be y. Okay, so let's try to zoom in here to get an idea of what's happening. Okay, so AB and CD are 2x. Since these are the midpoints, so this is x, this is x, this is x, this is x. Similarly, AD and BC are of length 2y, and since these are the midpoints, these segments are going to be of y and y. So that is what is happening. Now I'm going to do a construction. What will be that construction? So point number 2, construct, or rather join. Okay, construct the line HF. Okay, I'm going to construct the line HF. So let's use the same color, and I'm going to draw this line HF here. Okay, so this line HF. Now it's okay. At the same time, we are going to connect. Okay, wait, hold on. Let's not connect all the midpoints. So we are constructing the line HF. Now let's consider this triangle HGF. Okay, in fact, let me use straight lines so it looks better. Okay, now focus on this triangle focus on this triangle HGF and this line HF. Okay, so if you look at this quadrilateral, okay, in fact, let's do one thing. Let me create a copy of this so that it's easy to explain, because this diagram has lot of information and it's confusing. So let's come here, okay, and paste. Yes, now there are certain things which I don't want, so we'll just erase them. Okay, so first of all, I don't want this, and this. Okay, yes, this is what I want us to focus on. Now we have constructed the line HF, the constructed line HF. Now, okay, consider the quadrilateral. Okay, which quadrilateral? This quadrilateral, which, okay, HFCD. Consider the quadrilateral HFCD. Okay, so we have in this quadrilateral we have HD is equal to FC. Okay, the opposite sides are equal to each other. Why? Because Y, their length is Y, and we also have HD as parallel to FC. Why is that so? Because AD is parallel to BC, which is the parallelogram, original parallelogram. So HD and CF are part of these two longer parallel lines. So in this quadrilateral, now let's use a highlighter. Okay, in this quadrilateral, we have these opposite sides. Okay, these opposite sides equal and parallel to each other, and this is an important condition which proves that this quadrilateral is a parallelogram. Okay, and thus quadrilateral HD, oh, I'm going to say HDFC. So quadrilateral HFCD is a parallelogram. Now this is an important conclusion in this proof, that this small parallelogram, the small quadrilateral is a parallelogram. Okay, so once we prove that it is a parallelogram, thus, so now point number 3. So now HF is parallel to DC. Okay, because they are opposite sides of a parallelogram. Now let me remove the highlighted part so that it's easy to understand. Okay, so we have HF. Okay, let's remove this also. We have this HF as parallel to DC. Okay, so line HF is parallel to line DC, and in this parallelogram, with the same base as HF, we have another triangle inside it. So it's a triangle which has the same base HF, and it is between the same two parallel lines as the parallelogram. So we know an important proof with this condition, that this triangle will be half of the area of this parallelogram. Why? Because both parallelogram and the triangle have a common base HF, and they are between the same parallel lines. Okay, so we are going to use the theorem and conclude the so now HF is parallel to DC, and I'm going to write here triangle HFG is between same parallel lines as HFCD. Okay, so therefore area of triangle HGF will be half the area of parallelogram HFCD. Okay, this is a very important statement, very important conclusion in our proof. Area of triangle HGF is half the area of this parallelogram HFCD. Okay, now coming back to the original figure. This was the original figure. Now what? So we consider this. Yes. So we consider this parallelogram and this triangle. Okay. Now what we are going to do? We are going to consider this lower half of the parallelogram, and we will construct another triangle here. So once again, let's come down, and in fact, let's make a copy of it. So yes, let's erase the unnecessary parts. Okay. So I don't need this, I don't need this, I don't need this, I don't need this, and I also don't need this orange line. I don't need. I need the blue line. Okay. So HF is the line which we constructed. Now what we are going to do is we are going to construct this triangle here. Okay, HEF. And once again, I am not going to repeat the whole proof, but the concept is exactly same. Even here we follow the same procedure. Okay, the same procedure as and we are going to follow the same procedure here. So even here we can prove that this is a parallelogram. Okay, that will be our step 1. So let me make a note of it. Okay, so I'm just going to quickly note down the points. So first point is that AH is parallel to BF and AH is equal to BF. Okay, therefore HABF is a parallelogram. Okay, so once we know it's a parallelogram, then point number two is so line HF is parallel to line AB. Why? Because they're opposite sides of a parallelogram. And then we have EF. Now again, okay, we have a triangle HEF. So let's highlight it. This is the triangle HEF. Okay, this triangle uh, and the parallelogram HABF. Okay, I'm going to use another highlighter. So HABF, this parallelogram, both the triangle and the parallelogram, they have common base or same base. They have common base, which is HF, and they lie between same parallel lines. Okay, therefore, oh, we are short of space. Okay, therefore, so I'm going to write okay, let's create a space here. Therefore, I'm going to use another color. Therefore, we can say area of triangle HEF, is equal to half the area of parallelogram, which is a parallelogram HABF. This is an important conclusion. Second important conclusion in our proof. So I'm going to box it. So these two important conclusions we have, that that area of triangle HGF is half of HFCD, area of triangle HEF is half of HABF. So let's come to our original. Yes, now what we can do is, yes, we can construct this line also here. So this is the line and this is the line. Okay, now what I'm going to do is I'm going to add both these equations. Okay, what is HGF? So this is HGF plus HEF. So this is HEF. Okay, that is equal to this whole quadrilateral HEFG. Okay, and I'm going to add these two sides also of the equations. So let's do it. Since we are short of space, it's a bit confusing, but let's try. So let this, okay, let okay, let this be equation number 1 and let this be equation number 2. Okay, so I'm going to add. Now this is going to be a little tricky, but let's do it. So what I'm going to do is, okay, so I'm going to write here add equations 1 and 2. Okay, we're going to add equations 1 and 2. So visualization is important. Oh, I didn't complete this line. Okay, let's complete this line. So this is that line. So visualization is important. So when we add these two equations, HGF and HEF. So HGF and HEF. On the left hand side, I'll get the parallelogram. So on left hand side, we after adding we'll get the parallelogram EFGH, and on right hand side we'll get half of. Okay, now HFCD, which is this HFCD plus HABF. So HABF, if you add these two small parallelograms, you get the whole big parallelogram ABCD. So on the left hand side we have half of parallelogram ABCD. Okay, half remains. Don't confuse, half plus half will not be equal to 1. This is half plus half, half is the common, and we add these two parallelograms. So the adding these two small parallelograms will give us a big parallelogram ABCD. So thus we have proven that parallelogram EFGH will be half of parallelogram ABCD, which is exactly what the question had asked us to prove.